Welcome to this comprehensive mathematics lecture on logarithms, designed specifically for students eager to understand the power of mathematical compression. Historically, logarithms were co-invented in the early 17th century by John Napier and Henry Briggs to simplify complex astronomical calculations. In an era before computers, multiplying large numbers or dividing them took hours of tedious manual computation. Napier realized that by mapping multiplication to addition, calculations could be sped up enormously. Today, logarithms are not just a historical computational tool. They are a fundamental mathematical language used to describe phenomena that span vast physical scales, from the tiny concentrations of hydrogen ions in chemistry to the massive energy release of tectonic plates in earthquakes. By mastering logarithms, we gain a tool that compresses exponential curves into straight lines, letting us analyze the universe's scaling behaviors with ease. To understand logarithms, we must first look at them as the direct mathematical inverse of exponents. In exponential arithmetic, we start with a base, raise it to an exponent or power, and compute the resulting value. For example, 2 raised to the power of 3 equals 8. The logarithm asks the exact opposite question. To what power must we raise a base of 2 to obtain a value of 8? The answer is 3. Mathematically, we write this as log, base 2, of 8 equals 3. This gives us the foundational equivalence. B raised to the power of y equals x is equivalent to log, base b, of x equals y. Here, b is the base, x is the argument or value, and y is the logarithm or exponent. Note that because we only define real logarithms for positive bases, the argument x must always be strictly greater than 0. The true mathematical magic of logarithms lies in their operational properties. Because logarithms represent exponents, they follow the laws of exponents in reverse. Let us examine the first 2 major properties, the product rule and the quotient rule. The product rule states that the logarithm of a product of 2 numbers is equal to the sum of their individual logarithms. That is, log of m times n equals log of m plus log of n. This is why John Napier's work was so revolutionary. It allowed ancient astronomers to multiply large numbers simply by adding their logarithms. Similarly, the quotient rule states that the logarithm of a quotient of 2 numbers is the difference of their logarithms. Log of m over n equals log of m minus log of n. These rules allow us to split complex calculations into simple, linear parts. Continuing our exploration of logarithmic properties, we encounter 2 more essential equations, the power rule and the change of base formula. The power rule states that the logarithm of a number raised to an exponent is equal to that exponent times the logarithm of the number. Mathematically, log of m raised to the power of k equals k times log of m. This property is incredibly powerful for solving equations where the variable is trapped in the exponent. Next is the change of base formula. Historically, calculating logarithms for arbitrary bases like base 7 or base 12 was difficult because tables were only printed for base 10. The change of base formula states that log base b of a equals log base c of a divided by log base c of b. By choosing c as 10 or the natural constant e, we can evaluate any logarithm using standard scientific tools. In science, engineering, and daily mathematics, the most frequently used logarithm is the common logarithm, which uses a base of 10. When we write log of x without specifying a base 10 is always implied. Common logarithms are directly tied to our base 10 decimal system and scientific notation. Every positive number x can be written in scientific notation as a mantissa m between 1 and 10, multiplied by 10 raised to an integer power c. Taking the common logarithm of both sides, we get log of x equals c plus log of m. The integer part c is called the characteristic, and it tells us the order of magnitude of the number. The decimal part log of m is called the mantissa, which represents the precise digits of the number. This structure allows us to represent numbers that span millions or billions on a compact, human-readable scale. While base 10 is highly intuitive for decimal counting, nature itself operates on a different fundamental base, Euler's constant, e. approximately equal to 2.71828. The logarithm with base e is called the natural logarithm and is written as ln of x. The number e represents the limit of continuous growth, and it appears organically in calculus, biology, physics, and financial interest calculations. If a quantity grows at a rate proportional to its current size, its growth is described by exponential base e, and the time required to reach a certain size is computed using the natural logarithm. Whether we are calculating the radioactive decay of carbon atoms to date ancient relics, or modeling the exponential growth of cells in a laboratory dish, the natural logarithm is the primary mathematical tool we use to track continuous change. One of the most remarkable aspects of logarithms is how they appear across multiple scientific disciplines to measure things that span massive scales. In chemistry, the acidity of a liquid is measured on the pH scale. The concentration of hydrogen ions can span from 10 to the minus 14 to 1. By defining pH as the negative common logarithm of the hydrogen ion concentration, we compress this vast chemical range into a simple scale from 0 to 14. In physics, sound intensity spans trillions of units. We measure sound level in decibels using a logarithmic ratio, where every increase of 10 decibels represents a tenfold increase in actual sound wave energy. Similarly, in geology, the Richter scale measures earthquake magnitude. A magnitude 7 earthquake has a wave amplitude 10 times larger than a magnitude 6, and releases about 32 times more energy, showing how logarithms help us comprehend massive physical forces. Now let us apply our understanding to solve algebraic logarithmic equations. The standard method is to isolate the logarithms, apply properties to combine them, convert the equation into its equivalent exponential form, solve for x, and finally verify that our solution is within the mathematical domain. Let us solve. Log base 2 of x minus 3 plus log base 2 of x plus 3 equals 4. Using the product rule, we combine the logs into log base 2 of x squared minus 9 equals 4. Next, we exponentiate x squared minus 9 equals 2 raised to the power of 4, which is 16. Adding 9 to both sides, we get x squared equals 25, yielding x equals 5 or x equals minus 5. We must verify these roots. Substituting x equals 5 gives valid positive arguments. However, substituting x equals minus 5 results in taking the log of a negative number, which is undefined. Thus, we discard minus 5 and conclude the only solution is x equals 5. To conclude our theoretical journey, let us review all the core formulas on our dashboard. We have defined the inverse relationship between exponents and logarithms, where b raised to the y equals x is equivalent to log base b of x equals y. We have established that log of 1 is always 0 and log of the base is always 1. We have mastered the product rule, the quotient rule, the power rule, and the change of base formula. Remember that when solving equations, checking the domain of your arguments is not optional. It is a critical step to avoid incorrect extraneous answers. These formulas form the complete foundational toolbox for advanced mathematics, calculus, and scientific analysis.